Welcome to today's problem walkthrough. In this session, we'll explore problem number 1053, titled Previous Permutation with One Swap. This is an interesting problem that challenges your understanding of permutations and array manipulation. Let's dive in and break it down step by step. In this problem, you are given an integer array ARR of size n, and a permutation of this array is simply any reordering of its elements. The goal is to determine the previous permutation of the array, which is the largest permutation that is strictly smaller than the current array in lexicographical order. For example, if the input array is 3, 2, 1, the previous permutation would be 3, 1, 2. However, if no such permutation exists, meaning the array is already the smallest possible order, the array should remain unchanged. Importantly, you can only achieve this by swapping at most one pair of elements. The task is to write a function that returns the resulting array after performing this operation if possible, or the original array if no swap can create a smaller permutation. The constraints ensure that the array size can go up to 10,000, and each element in the array lies between 1 and 10,000. Let's look at the first example. Here, the input array is 3, 2, 1. The output is 3, 1, 2. The explanation is that 3, 1, 2 is the largest permutation that is smaller than 3, 2, 1 when compared lexicographically. To achieve this, we only need to swap the elements 2 and 1. Now consider the second example, where the input array is 1, 1, 5. In this case, the output is 1, 1, 5, because the array is already in its smallest possible permutation. No swap can make it smaller, so the array remains unchanged. Now, let's examine the third example. The input array is 1, 9, 4, 6, 7, and the output is 1, 7, 4, 6, 9. To explain this, the permutation 1, 7, 4, 6, 9 is the largest permutation smaller than 1, 9, 4, 6, 7 in lexicographical order. To achieve this, we only need to swap the elements 9 and 7. Additionally, it's important to note that the constraints of the problem allow us to work with arrays of length up to 10,000, and the values in ARR are guaranteed to be between 1 and 10,000. When considering edge cases, there are a few key scenarios to keep in mind. First, if the input array contains only one element, such as 5, the output will also be 5, since a single element array cannot have permutations, and no swap is possible. Second, if all elements in the array are identical, such as 2, 2, 2, the output remains 2, 2, 2, because all permutations of the array are identical, and no swap can change its order. Third, if the array is already sorted in ascending order, like 1, 2, 3, it is already the smallest permutation, so the output is 1, 2, 3. Lastly, for a larger array such as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, the output would be 10, 9, 8, 7, 6, 5, 4, 3, 1, 2 after swapping the last two elements. In the case of the larger array example, swapping the last two elements, 2 and 1, results in the largest permutation that is smaller than the original array. This demonstrates how a single swap can be used to find the desired permutation efficiently, even for arrays at the upper limit of the input constraints. By carefully identifying the right elements to swap, the solution ensures that the resulting permutation meets the problem's requirements while adhering to the constraints. To start, let's consider the brute force approach for solving this problem. The idea here is to generate all possible permutations of the given array that are lexicographically smaller than the original array. Once we have all these permutations, we would then identify the largest one among them that satisfies the condition. While this method guarantees correctness, it comes at a steep computational cost. Generating all permutations of an array has a factorial time complexity, which means the number of operations grows extremely fast as the array size increases. On top of that, comparing and storing permutations introduces additional overhead. As a result, this approach becomes impractical for larger arrays, making it clear that we need a more efficient solution to handle this problem effectively. Now let's explore the optimized approach, which is both efficient and well suited for this problem. The key here is to minimize changes to the array while still making it lexicographically smaller. To achieve this, we focus on a single adjacent swap. The crucial insight is to locate the rightmost decreasing pair of elements in the array, as this is the first place where the array stops being non-increasing in reverse order. From there, the steps are straightforward. First, identify the element at this breakpoint, ARR, I, and then find the largest element to the right of it, ARR, J, which is smaller than ARR, I. By swapping these two elements, we ensure the result remains as large as possible while still being smaller than the original array. This approach is highly efficient, requiring only two traversals of the array, resulting in a linear time complexity of O(n). It avoids unnecessary computations and directly targets the desired result, making it a practical and scalable solution. The optimized approach stands out as the clear choice for solving this problem, and here's why. First, in terms of efficiency, the linear time complexity ensures that the solution can handle larger input sizes without performance issues. Second, the approach guarantees correctness because it leverages the structure of the array to find the lexicographically largest permutation smaller than the original, using just a single swap. Additionally, its simplicity is a major advantage. With only a couple of traversals and one swap, the algorithm is both easy to understand and implement. Comparing this to the brute force approach highlights the trade-offs. While the brute force method is exhaustive and guaranteed to work, its computational cost makes it infeasible. The optimized approach, on the other hand, avoids unnecessary calculations by focusing on the rightmost decreasing pair. The key insight here is that making a change at the smallest possible index, RR, I, ensures the result is as close as possible to the original array while still being smaller. This focus on the rightmost decreasing element, coupled with swapping it with the largest valid candidate, is what makes this approach both elegant and efficient. In conclusion, the optimized approach captures the perfect balance between correctness, efficiency, and simplicity. By leveraging the structural properties of permutations, it eliminates the need for brute force and directly solves the problem in linear time. This makes it a highly practical solution for real-world scenarios. With its clear steps and logical flow, it ensures that we achieve the desired result with minimal computation. Ultimately, this approach not only adheres to the problem constraints but also highlights the power of focusing on key insights to simplify complex problems. The problem asks us to find the largest permutation of an array that is still smaller than the given array. If no such permutation exists, meaning the array is already the smallest possible arrangement of its elements, we simply return the array as it is. To solve this, the first step is to identify the rightmost decreasing element. By traversing the array from right to left, we look for the first index, I, where the current element is greater than the next one, that is, I plus 1. This marks the pivot, which is the element that disrupts the descending order. Identifying this pivot is crucial because it signals the point where the permutation can be adjusted to find a smaller configuration. If no such element is found during the traversal, it means the array is already in ascending order, which is the smallest permutation, so we return the array directly. Once the pivot is identified, the next step is to find the largest element smaller than the pivot. Starting from the rightmost end of the array, we look for the largest index j such that ARR, j, is less than the pivot, ARR, I. This ensures that swapping these two elements results in the largest possible decrease in the array's value while still maintaining the condition of being smaller than the original array. After identifying this element, we proceed to swap ARR, I, and ARR, j. This is done to adjust the prefix of the array, replacing the pivot with the optimal candidate that minimizes disruption. The final step is to reverse the portion of the array from I plus 1 to the end. Reversing this suffix guarantees that it is in descending order, making the resulting array the largest possible permutation that is still smaller than the original. By combining these steps, we ensure the solution is both correct and efficient. To summarize the key insights of the algorithm, first, identifying the pivot is essential as it highlights where the current permutation can be modified to make it smaller. Second, the swap is carefully chosen to ensure minimal disruption by selecting the largest smaller element, which keeps the result as close as possible to the original while meeting the problem's requirements. Third, reversing this suffix is a critical step to ensure that the array's tail is rearranged into its largest descending order, giving the final configuration. Edge cases are also important to consider. For example, if the array is already in ascending order, it is the smallest permutation, so no changes are needed. The algorithm leverages in-place modification of the array, using two pointers, I and j, to efficiently navigate the array and perform the necessary operations. The algorithm is efficient, with a time complexity of O(n). This includes O(n) for finding the pivot, O(n) for identifying the element to swap, and O(n) for reversing the suffix, resulting in a total time complexity of O(3n), which simplifies to O(n). The space complexity is O(1), because all modifications are done in place, with no additional data structures required. This makes the solution both time-efficient and space-efficient, suitable for large input arrays. Let's walk through an example to see how the algorithm works. Given the input array ARR equals 3, 2, 1, the first step is to identify the pivot. Traversing from the right, we find that the first index where I plus 1 is I equals 0, as 0, 1. Next, we find the largest element smaller than the pivot. Starting from the rightmost end, we locate j equals 2 because 2, 0. Then, we swap these two elements. Swapping 0 and 2 results in the array becoming 1, 2, 3. Finally, we reverse the suffix starting at index I plus 1, which is 1. Reversing this portion gives the final array 1, 3, 2. Thus, the output is 1, 3, 2. Now, let's address some edge cases. If the input array is already the smallest permutation, such as equals 1, 2, 3, no smaller permutation exists, so we return the array as is. For single-element arrays, like equals 1, the output remains 1, since there are no other elements to rearrange. Similarly, if all elements in the array are identical, such as equals 2, 2, 2, no smaller permutation exists, so the array is returned unchanged. These edge cases highlight the robustness of the algorithm, ensuring it handles all possible scenarios gracefully. This Python implementation solves LeetCode problem number 1053, previous permutation with one swap, efficiently. The goal is to find the largest permutation smaller than the given array using a single swap. Explanation. Step 1. The algorithm begins by identifying the rightmost index I where I plus 1. This ensures we locate the first decreasing element when traversing from right to left. If no such index exists, i.e., the array is non-decreasing from left to right, the array is already the smallest permutation, and we return it as is. Step 2. If we find a valid index I, the next step is to find the largest index j greater than I where I. This ensures that swapping I and j results in the largest possible permutation smaller than the original. Additionally, to handle duplicate values, we move j leftward to ensure we pick the rightmost occurrence of j for the swap. Step 3. Finally, the algorithm performs the swap between I and j. This single operation guarantees that the resulting permutation is the desired one. The algorithm has a linear time complexity of O(n), because we perform at most 2 linear scans of the input array. This makes it efficient and well suited for the problem requirements. Edge cases. 1. If the array is already in ascending order, it is the smallest permutation, so no swap occurs. 2. If the array has duplicate elements, the algorithm ensures correctness by handling rightmost occurrences appropriately. 3. Single-element arrays or arrays with no decreasing pairs return as is. This implementation is robust, handles edge cases effectively, and adheres to the problem constraints. Here we begin the implementation of the previous permutation with one swap problem in Java. First, we import the necessary utilities and define the solution class, which contains our main method, prevPermOpt1. The method takes an integer array, as input and returns the modified array. We start by determining the length of the array and initializing the variable I to n2. The goal is to find the rightmost index where the current element is greater than the next one. This is done using a while loop that decrements I until the condition I plus 1 is met. If no such index exists, meaning the array is already the smallest permutation, we simply return the array as is. Next, we move on to find the largest index j, position after I, such that j is less than I. To do this, we initialize j to the last index and decrement it while j is greater than or equal to I. Additionally, to ensure that we swap with the rightmost occurrence of j, we continue moving j leftward if the previous element equals j. Now that we have identified the indices I and j, we proceed to the final step of the algorithm, which is swapping the elements at these indices. We store the value of I in a temporary variable, then assign j to I, and finally place the stored value from temp into j. This completes the swap, effectively giving us the largest permutation that is smaller than the given array. With the swap complete, we return the modified array as the result. This straightforward approach ensures the array is transformed correctly with a time complexity of O(n), making it efficient for solving the problem. To solve the problem, we start by identifying the rightmost position in the array where the current value is greater than the next one. In this example, the input array is 3, 2, 1. Here, we initialize I to n2, which is 1, and compare 1 equals 2 with 2 equals 1. Since 2 is greater than 1, we stop, and the rightmost index I is determined to be 1. Next, we look for the largest index j that is greater than I, where j is less than I. We start with j equals n1, which is 2, and compare 2 equals 1 with 1 equals 2. Since 1 is less than 2, we stop, and the largest index j is found to be 2. Finally, we swap I and j, which means swapping 1 and 2. This transforms the array into 3, 1, 2. Hence, the output for this example is 3, 1, 2. Now, let's examine a slightly larger input array 1, 9, 4, 6, 7. The goal remains to produce the previous permutation by performing one swap. We begin by finding the rightmost index I where I is greater than I plus 1. Here, we start with I equals 3 and compare 3 equals 6 with 4 equals 7. Since 6 is not greater than 7, we decrement I to 2 and compare 2 equals 4 with 3 equals 6. Again, 4 is not greater than 6, so we decrement I to 1. This time, we compare 1 equals 9 with 2 equals 4. Since 9 is greater than 4, we stop, and the rightmost index I is determined to be 1. Next, we look for the largest index j greater than I where j is less than I. Starting with j equals 4, we compare 4 equals 7 with 1 equals 9. Since 7 is less than 9, we stop, and the largest index j is found to be 4. Finally, we swap I and j, which means swapping 1 and 4. This updates the array to 1, 7, 4, 6, 9. Therefore, the output for this example is 1, 7, 4, 6, 9. Finally, let's look at an input array where no swap is needed, 1, 1, 5. To determine this, we first find the rightmost index I where I is greater than I plus 1. Starting with I equals 1, we compare 1 equals 1 with 2 equals 5. Since 1 is not greater than 5, we decrement I to 0 and compare 0 equals 1 with 1 equals 1. Again, 1 is not greater than 1, so we decrement I to minus 1. At this point, no such index I is found, which means the array is already the smallest permutation possible. As a result, no swaps are needed, and the output remains 1, 1, 5. To analyze the time complexity of the algorithm for solving the previous permutation with one swap problem, let's consider the key steps involved. First, we need to find the rightmost index I where the value at I is greater than the value at I plus 1. This requires a single pass through the array, moving from right to left. In the worst case, the loop will traverse all n elements, resulting in a time complexity of O(n). Next, we identify the largest index j that is greater than I such that j is less than I. This step involves another pass through the array, starting from the rightmost element and moving back toward I. Again, in the worst case, this loop iterates through all n elements, contributing another O(n) to the time complexity. Additionally, we need to ensure that the rightmost occurrence of j is selected. To do this, we perform one more pass, moving leftward from the identified j until the condition is met. Like the previous steps, this can involve up to n iterations, adding another O(n) to the total time complexity. Following the identification of indices I and j, the algorithm performs a swap between the elements at these two positions. The swapping operation itself is constant time, requiring no iteration, so its time complexity is O(1). When we sum up the time complexities of all these steps O(n) for finding I, O(n) for finding j, O(n) for ensuring the rightmost occurrence, and O(1) for the swap, the total becomes O(3n). However, in big O notation, constant factors are ignored, so the overall time complexity simplifies to O(n). This linear time complexity ensures that the algorithm efficiently handles the input even for large arrays. Now turning to space complexity, this algorithm is designed to work in place, meaning it modifies the input array directly without creating any additional data structures. The only extra memory used is for a few integer variables, such as I, j, and n, which are used to store indices and the array length. Since these variables require a constant amount of space, the auxiliary space complexity is O(1). While the input array itself occupies O(n) space in memory, this is not considered additional space because the array is part of the input. Therefore, the overall space complexity of the algorithm is O(1), making it highly space efficient. When analyzing the algorithm across different scenarios, we observe distinct cases. In the best case, the input array is already the smallest possible permutation, such as 1, 2, 3, 4. Here, the algorithm quickly determines that no I exists where I plus 1, completing the process in O(n) time. In the average case, the algorithm typically performs the three main linear scans, one each for identifying I, finding j, and ensuring the rightmost occurrence. These steps collectively result in a time complexity of O(n). In the worst case, the algorithm must traverse all elements in each of the three linear scans. For example, an array like 4, 3, 2, 5, 1 might require full passes through the array to resolve all conditions, but even then, the time complexity remains O(n). Comparing the optimized algorithm to a brute force approach highlights its efficiency. A naive solution would generate all permutations of the array, sort them, and then identify the largest permutation smaller than the current array. Generating all permutations has a time complexity of O(n), and sorting them would add an additional O(n). Log n, making this approach computationally infeasible for even moderately sized arrays. In contrast, the optimized algorithm entirely avoids generating permutations. By using a greedy strategy in linear scans, it achieves a time complexity of O(n), which is exponentially faster. Mathematically, each step involves at most a single pass through the array, and the constant factor in O(3n) is dropped in asymptotic analysis, simplifying to O(n). With minimal space usage requiring only a constant number of extra variables, the space complexity is O(1). This combination of linear time and constant space makes the algorithm optimal for this problem. A common pitfall when solving this problem is not handling edge cases properly. For example, consider an array like 1, 2, 3, which is already the smallest permutation. If your algorithm doesn't account for cases like this, it might return invalid results or even throw an error. Similarly, single-element arrays or arrays that are already sorted in ascending order are edge cases that require careful handling. Another frequent mistake is performing incorrect lexicographical comparisons. Remember, lexicographical order is determined by sequentially comparing elements, much like dictionary order. Misinterpreting this can result in the wrong output. Finally, some implementations rely on brute force approaches, generating all possible permutations and then filtering for the correct one. While this method may seem straightforward, it's highly inefficient with a time complexity of O(n), which becomes impractical for larger arrays. Avoiding these mistakes is key to crafting an effective solution. Another mistake to watch for is modifying the original array prematurely. If you alter the input array before determining the correct permutation, you risk data loss and incorrect results. It's best to work on a copy of the array unless specifically instructed otherwise. Additionally, overlooking sorting constraints can lead to errors. After performing a swap, the portion of the array that follows must be sorted to ensure the result is the largest valid smaller permutation. If you skip this step, the output may fail to meet the problem's requirements. Paying attention to these details will help you avoid common pitfalls and produce a robust solution. To excel in interviews, it's helpful to understand the structure of lexicographic order. A key insight is identifying the pivot. This is the first element from the end of the array that breaks the decreasing order. Once you find the pivot, you can adjust the subsequent elements to find the correct permutation. Instead of generating all permutations, focus on efficient swaps. After identifying the pivot, swap it with the largest smaller element in the suffix and then reverse the suffix to achieve the desired result. Problems involving permutations often rely on patterns like sorting, reversing, or partitioning the array, so recognizing these can give you an edge. During interviews, it's also important to clearly communicate why your solution works optimally. For instance, you might explain that sorting the suffix minimizes complexity while ensuring correctness. For additional practice, related problems like next permutation, permutations, and next greater element 3 are excellent resources to strengthen your understanding of these concepts. There are alternative approaches to solving this problem, each with its own trade-offs. A brute force method involves generating all permutations recursively, then filtering and sorting to find the desired result. While this approach is simple to implement, it's highly inefficient with a time complexity of O(n). A more optimized method uses a two-pointer approach. This involves identifying the pivot, swapping it with the largest smaller element, and then reversing the suffix. This method is significantly more efficient with a time complexity of O(n), but it does require careful implementation to avoid errors. For even greater efficiency, you can use binary search on the suffix to find the largest smaller element instead of scanning linearly. This reduces the search time to O log n for that step, though it adds some complexity to the implementation. Each approach has its place, so choose the one that best balances simplicity and efficiency for your needs. Great job following along. To recap, we explored the problem, broke it into manageable steps, and discussed an optimal solution. Remember to practice similar problems to strengthen your grasp of array manipulation and permutations. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!